Okay, so in this video, we're going to keep expanding our knowledge of magnets. Okay, in the last video, we just simply talked about what was magnetism, just a little bit of review, basically from middle school science, right? So now we're going to talk about the magnetic field, right? And how does it affect certain things? Okay, so a magnetic field, right, that we call the B field, is a vector that describes a magnetic influence on moving electric charges, electric currents, and magnetic materials. So magnetic fields will have these different properties. So a magnetic field is created at all points in space surrounding a current carrying wire. Okay, so here's our kind of combination or our link between electricity and magnetism. So if we have a current carrying wire, we are creating a magnetic field around the wire. Right. So the magnetic field at each point is a vector. So this is one of those famous vector fields. It has both magnitude, which we call the magnetic field strength, or B, and a direction. Much like when we talked about electricity, so they had the electric field, which was a vector field surrounding a point charge, or current, or excuse me, not current, but around electrical charge. We have the same thing, right? So if we have a magnet, we have a magnetic field. If we have a current carrying wire, we have a magnetic field that has a magnetic field strength of B, okay, and it points in a direction. And we'll talk about the direction here in 1 second. So the magnetic field will exert forces on magnetic poles. Okay, the force on the North Pole is in the opposite, or excuse me, in the same direction as to the magnetic field, while the force in the South Pole is in the opposite direction. Okay, and so if I have if I have a current carrying wire, right, and it's a square wire. Okay, so if I have a current carrying wire and I have a point here, okay, the force, if this is so let me put it this way. So if this is a magnet, right, not a current carrying wire, let's just talk about magnet in general. So if this is a magnet, we have these magnetic field lines that go out of north and into south, right? So if I put another magnetic material right here, okay, the north will point in the same direction, right? So the B field will point in the same direction, right, as the excuse me, the force. We'll put force. So FB will point in the same direction if this was a north, uh, kind of, in this one it's north, and if this is a south, so this would be a north particle. This is a south particle, right? And so it would point in the opposite direction as the field, right? So again, we're looking at field versus um, force, okay? And so another way to picture the field is with the use of magnetic field lines. All right, and so a tangent to a field, okay, is in the direction of the magnetic field line. The field lines are closer together where the magnetic field is larger. It's the same thing with, so there's a lot of parallels between electricity and magnets. Okay, just like we said, the closer the E field lines were, the stronger the E field was there. It's the same thing. The closer the magnetic field lines are, the stronger the magnetic field. So to determine the direction of a magnetic field around a current carrying wire, we're going to use, just like we've done in other things, we're going to use the right hand rule. Okay, so this process is a little bit different before because all you need to know is the direction of the current, uh, and that will tell you. Okay, so if I know the direction of the current, I can give you which direction the magnetic field goes. So, okay, so all we're going to do is going to take your right hand, right, point your thumb in the direction of that current, and your fingers are going to curl around it, and that's going to be the way that they point. That's the direction of the field. Okay, so we're going to point your right, and this That's the word that we should be filling in here. So your right thumb in the direction of the current. Curl your fingers around the wire to indicate a circle, and your fingers are going to point in the direction. Uh, and I already had the word point in there, but it's going to, this word should be direction. Okay, it's going to um, point in the direction of the magnetic field lines around the wire. Okay, so if we look at this little diagram here, so the red indicates north. And you can see how this works. So your magnetic field line is always going to point in the direction of north, right? So it's always, that's the direction it's going to go. So if I have a current carrying wire, which again, remember the X means into, the dot means out. Okay, so here we have current going into the page. So I take my thumb, I'm going to pretend I'm on my iPad, right? So I'm going to take my thumb, point it in the direction of the current, okay? And I curl my fingers. So if this is coming, if it's into the page away from me, right? And then I curl my fingers and know that my fingers curl in this manner, right? And the thing to note is that your fingers curl in the direction of the north, okay? So my field will be concentric circles, right? In this manner, right? In this case, going counterclockwise, or excuse me, clockwise, because going in, right, curls my fingers in the clockwise direction. And so just think about like these concentric circles running around this wire, okay? But one thing to note, if I take compasses, this is going to point in the direction of north, right? And so these little red arrows mean north, okay? And you can see that it matches that counterclock, or excuse me, that clockwise motion. So if I did out of the page, they would go in the opposite direction. If I did right to the left, to the right, okay, again, it's going to follow. My fingers are going to curl in that direction, okay? Now, the magnetic field lines will always point from north to south. So anytime you draw a magnetic field line, okay, you're pointing in the north, in the north to south direction. So okay, so it's the same way in the idea that electric field lines went positive to negative. So it's the same exact idea. Okay, so if you want to think about it, the north is kind of the positive end, right? The south is kind of the negative end. Now, the SI unit for magnetic field strength is the Tesla, capital T. It's named after Nikola Tesla. I think he may not have a C in his name. Okay, who did a lot of work in really in the field of electromagnetism. Um, all right, so now we're going to look. So concludes this is just a general video on magnetic fields. Now we're going to look at specific fields, and you can see kind of popping out the bottom page. We're going to look at what is the magnetic force on a moving charge, and then we're going to talk about current carrying wires and so forth.